So we have already written what's a truss. What is a truss? Rigid, short bars are members. Why I'm taking only short bars? Because as the length increases, the deflection increases at a very higher rate, right? So deflection is proportional to LQ. So as the length increases, deflection increases at a very higher rate. So we go with what? Short bars are members. Rigid short bars are elements. I'll say rigid short bars are members. Are elements. Rigid short bars are members are elements. Rigid short bars are members are elements. Connected by what joints? Hinge joints, because at that first, whatever they started, they have only hinge joints. After they went for riveted, welded, all these things, fixed joints. But what happened is, for analysis purpose, it's very difficult to do analysis of a welded joint or a riveted joint at this stage. So what we did is, for the time being, whatever is given, we'll assume it as a hinge joint and solve the problem. Okay, so rigid short bars are members. Rigid short bars are elements connected by hinge joints. Connected by hinge joints. How are they connected? By hinge joints to form a triangular framework. Why a triangular framework? I have shown yesterday, because that is the structure. The basic structure element is a triangle. To form a triangular framework. Is known as a truss. Are you okay? Is known as a truss. And I have also told you that the trusses will have only axial stresses. They won't have any. The members of the truss will not have any bending or shear stresses unless they are loaded on the members. Why and all I will show you. Okay. So the now target for us is what? Doing the analysis of these trusses. Now the target is what? Analysis of trusses. So generally analysis of trusses will be in different stages. That is, finding the loads in the members, then doing the stress analysis, then again doing the deflection analysis. There are many things, but at our level we have only one task. That is the only one objective we have. What is that objective? We have only one objective, that is to find force, or I'll say to find load, because the civil people use the same terminology. To find load in each member of the truss. To find load in each member of the truss. Sir, we will have the method to find for every member of the truss. But whatever he asked, for that we will do the problem. Okay. So to find load in each member of the truss. This is our target, right? So I have to know for the given loading conditions. They will say this is the given truss of this dimensions and these are the loads applied on it. In particular member, maybe A, B, B, C or some member, what is the load? Okay. So how to determine these loads in each member is only our target. Okay. And again subjected to what? Some idealizations or assumptions. What are those assumptions I am going to take? Because I am not again a chronopaid chicken biryani. Okay, chicken biryani is very far, sir. We are only here drinking milk. That's it. So what are all the assumptions I am going to make here? Sir, even in the exam, if that fellow has not given, I am taking these assumptions. By default, when a problem in truss is there, you can take these 5 assumptions. Okay, so maybe 3 assumptions and the 2 are conditions you can get from the problem. He will give only under those conditions. What are those? Number 1, all bars are treated as rigid. All bars are treated as rigid. All bars are treated as rigid. What do you mean by all bars are treated as rigid? In reality, they will have deflections, because none of this, see, in this world there is no rigid body at all, but as now we are not grown, we are not going to consider stresses or deflections, whatever is happening in them, we are not going to consider. So I'm going to take the all bars as rigid bars. All bars are treated as rigid. You may ask me, sir, they have deflection. That we will take at the next step level, okay? I mean, they will do after the load analysis, stress, and then after that, deflection, they will do the remaining analysis. For the time being, you have only loads, finding out the forces, where I'm going with the assumption, treating it as a rigid body. Are you okay? Are you okay? Next. And also one more is there. Sir, there may be some cases where we cannot even consider them. That analysis will become very complex. Then what we do? We go with one more thing, that is factor of safety. What is this factor of safety? When it becomes, see, I'm doing a truss, I have, and see, it's a very small bridge. There I cannot go with this FM analysis and all. It's a very smaller one. Then what we do? Instead of doing all those nonsense, let us say it takes 10 centimeters generally we got from the load analysis. We'll give some 12 or 13 extra, some 1.2 or 1.2 will keep the factor of safety. We'll give some extra cross section, extra dimensions, and then we will manage these things, right? So that is also we will be doing it. But for the time being, yes, there can be the further analysis, but we are treating it as rigid. All bars are treated as rigid. Next, all bars are considered to be massless. All bars are considered to be massless. All bars are considered to be massless. Why I am considering them as massless? See, compared to the loads coming onto them, these are less. But I won't say they are considerably less. They have weight, but at this level, I am also not considering their masses. Okay, but in the real problem, when you are doing it, you have to take them into consideration. Okay, so generally, I won't say they are negligible. They have certain mass. Because of those masses also there will be some deflections, they will affect it, but now at this level I am not considering them. Okay, I am treating them as massless. What are the two? All bars are treated as rigid, all bars are considered to be massless. Third one, all the joints are frictionless. All the joints are considered frictionless. All the joints are considered as frictionless. All the joints are considered as frictionless. All the joints are considered as frictionless. Sir, in reality, see, when you kept a hinge joint, they can move. When they move, what will happen? As they are moving, there is some friction between them. So, but if I take that frictional force into account, the analysis will become very complicated. So I am neglecting and treating it as frictionless. So these two assumptions are non-conservative assumptions. What do you mean by non-conservative assumptions? If because of these two assumptions, that means I'm treating it as rigid and I'm treating it as massless. If I treat accordingly and if I design the bridge, then what will happen is there is a chance of failure because I am neglecting these things. They will cause more trouble to me. They will cause damage to me. Because of them, whatever I'm designing, the structure is going to fail. There will be some extra burden on it or load on it. That's why these are non-conservative assumptions. I have to somewhere take them into consideration and again do the necessary corrections for it. But this assumption is conservative assumption. What do you mean by this conservative assumption? See, yesterday when I am doing, I told a simply supported beam will have a deflection less than A for the same load, same length, everything is same. Only the supports are changed from simply supported to friction. I'm sorry. A simply supported beam will have more deflection compared to a fixed beam. Everything is same. Cross section same, material same, load same, everything is same. When the supports are changed from simply supported to fixed beam, then definitely simply supported beam will have, because see, as there is no restriction at this hinge joints, it will bend like this. It can bend like this. But here what happens is they will apply some moment, they will offer some moment, and the deflection is going to be less, like this. Are you okay? That's why the slope at the fixed support will be 0. The slopes at the fixed supports will be 0, but hinge supports will have some slopes. They will allow it to rotate, so there will be a slope to the beam at the hinge support. Maybe when you go to strength of materials, already you might have done in second year of strength of materials in BTech. If not, you will do there. Okay, so Because of this reason, the deflection is less. Now, what happens if there is friction? What happens if there is friction? See, when the beam is going to bend like this, how is the frictional force? I have not yet explained, but how is the frictional force? Always opposite to the motion. As it is trying to go like this, the frictional force will be in the opposite direction. It will be in the opposite direction, and it will restrict the bending. So it will offer us resistance to not to bend. As it is giving resistance not to bend, the deflection compared to friction will be less than compared to non-frictionless. See, the deflection, if you treat it as frictionless, nobody is restricting it. So the deflection is, let us say, delta when it is frictionless. But what happens when there is a restriction? The deflection is going to be less. So which is more safe? Less deflection is definitely more safe than more deflection. Hence, this is a conservative assumption. What's the meaning of that? No need of taking factor of safety for this assumption. Even though you make this assumption, no need of taking factor of safety, because it will be more safe. Than whatever you are designing. But because of these things, it will not be safe. That's why we have to treat somewhere by using some factor of safety or something else to get them to make the design or structure safe. Are you okay? So these are majorly the assumptions. Remaining two. I have two more. What are those two more? Next, fourth one. What's that? The loads are applied. One sec. The loads are applied only on the hinges. That means only on the joints. Loads are applied only on the hinges. That means joints. That means I am not permitting to apply the loads on the members. If suppose there is a truss like this, if there is some truss like this, okay, I am not permitted. See, I can apply the load. This is the hinge joint. You can apply the load here. This is the hinge joint. You can apply the load here. But you are not permitted to apply the load here. This is not permitted. You cannot apply a load here. This is not permitted. Okay. On frames you can apply because they are having different things, but for our level we don't have these things. If any problem is given, just treat this as a simply two hinges beam, simply supported beam, and do it and go ahead. Okay, but never I have seen, sir, except once or while, but mostly I have never seen. 99% of the times giving it in the past 15 years I have never seen a problem like that. So yes, why I'm saying is it's possible. Maybe if you go for the highest structure analysis, yes, it is there, you can apply them. Okay, but at our level of basic mechanics, I don't have it. Okay, so we are only treating with the milk right now. So for me, so that's why I'm not saying it's an assumption. I'm giving that condition. What is that condition? Loads are applied only on the hinges. If they are not applied on the hinges, if they are applied on the members, then definitely this method needs some changes or needs some corrections to consider and take care of them. Okay, because if the loads are applied on the members, then again shear stress, bending stress will come into picture, and it's a different scenario that you will do only in the next level of structures and all. Okay, for my level, I am only treating, this is the basic structure, this is the basic truss. Later after getting riveted joints, welded joints and all, they started applying even on the members and all these things. Okay, so this is the basic truss. On the basic truss, loads are generally applied only at the hinges. Okay, so I'm only concerned loads are applied only on the hinges. Next, last assumption. What is the last one? This is also the condition. Okay, so I'm treating only with a, what's this? I'm not doing 3D problems, I'm only doing with the 2D. So 2D in the sense it's a planar truss. I'm not talking about a spatial truss. I'm not talking about a 3D truss. I'm only dealing with not a spatial truss. I'm only dealing with a 2D truss. That is a plane truss. As I'm only dealing with a plane truss, the loads on the members also should be within the plane of the truss. The loads on the truss also should be within the plane of it. Okay, all the loads should be within the all the loads should be within the plane of the truss. All the load should be within the plane of the truss. All the load should be within the plane of the truss. Okay, so what's the meaning of that is, see, if suppose this is my truss, maybe somewhere here it is a truss, I cannot apply the force like this, or like this, or I cannot apply, what's this, like this, somewhere from other directions I cannot apply. I have to apply the load only in the plane of the truss. Maybe here you can do whatever you want, but it should be here you can pull it, okay, here you can push it, these all are permitted, but it should be only within the plane of this, within this plane only you can apply it. You cannot apply like this and all, okay, this way. You cannot apply perpendicular truss or at some angle with the truss. Only the load should be within the plane of the truss. Okay, so under these five assumptions, I can, now I'm going to solve the problem. Okay, these are the assumptions, these are the conditions which I'm keeping. There are cases where you can violate them and have it, but now at our level of milk we don't have them. Okay, so all bars are treated as rigid, considered to be massless, considered to be all hinge joints are considered to be frictionless. Load should be within the hinge. Load should be only acting on the hinges or joints, and all the load should be within the plane of the truss. Okay, so all these five are satisfied, then I will do the analysis. Okay, so what is my objective? To find the load in the members. Okay, so there are two methods for this. What are the two methods? One is the basic method, one is method of joints, and second is method of sections. The first basic method is method of joints. There are two methods to find out the forces. One is method of joints. So first I will go with method of joints. First I will explain both method of joints and then method of sections. So after that, in problems, first I will do the problems on method of joints, and then I will show you why I have to go there with joints. Then I will go for the sections, and I will tell you why I prefer their sections. Okay, so now please all of you see here. Let us say I have been given with a truss like this. One sec. So this is the problem given to me. Okay, so I have a truss A, B, C, D, E. All members are having length L. At C I have a load W1. At D I have a load W2 making an angle theta with the horizontal. At E I have a load W3. So for the problem purpose, let us say I want to find the load in the member. FC. This is the target. Okay, some member we want, I'll take with FC. Okay, so I want to find the load in the member FC. Okay, so this is a truss given with this loading, and I want to find the load in the member FC. Okay, shall we start? Please all of you listen to me. Okay, so what's the first step? Consider step 1. Consider the entire truss to be a. Consider the entire truss to be a. Consider the entire. Sir, what are the method I'm going to do? This is the conventional method. Okay, first let me do in the conventional method, but problems I will only do in a faster manner, like how to do in the exam. Okay, but now let us learn the method. Okay, consider the entire truss to be a single body. And find the support reactions. This is the first step. Find the support reactions. What is the first step? Consider the entire truss to be a single body and find the support reactions. Consider the entire truss to be a single body and find the support reactions. Consider the entire truss to be a single body and find the support reactions. Now, how to get the support reactions? See, the procedure will be lengthy. We don't do this much in the exam while doing, but now for understanding, I'll go with the conventional method. Okay, so how to get the support reactions? For anybody, how to get the support reactions? First, draw the free body diagram. Free the body from everything and draw the sketch. One sec. Free the body from everything and draw the sketch. Free the body from everything and draw the sketch. Your wish. Whatever size you require, you draw to that size. Whatever size you require, you draw to that size. Okay. Free the body from everything and draw the sketch. Next. Free the body from everything and sorry. Free the body from everything and draw the sketch. Done. Next. Actions. What are the actions? See, there's a load W1 acting at C. There's one more load W2 making an angle theta with the horizontal. There's one more load W3 acting at E. Okay. Now I will take all of them at a time. Okay. Please, all of you see here. What's that? See, there's a load W1 acting at C. Next, there's a load W2 acting at this D at an angle theta with the horizontal. There's one more load W3 acting at E, right? So this is theta, W2, W1, W3. Okay. So these are the three loads acting on my truss, given truss. Sir, he has not mentioned any masses because we are treating them as massless, right? All are rigid. At every joint it is frictionless. Okay. So free the body from everything and draw the sketch. Done. Loads, 3 loads at CDE taken. Next, reactions. Actions done. Sketch done. Actions done. Go for the reactions. So what are the reactions? Tell me. At A I have a hinge support and at B I have a roller support. So what happens at the hinge support? It can offer maximum 2 support reactions. And roller support will offer maximum 1 support reaction in this direction. Are you okay? Now at A, this is in horizontal direction, so RAX. This is in the vertical direction or y direction, that is RAY. And this is RBY. Fill the body from everything and draw the sketch. Done. 3 loads are applied on the truss. I've taken all the 3 loads. 2 joints are there. One is the hinge joint, 2 support reactions maximum. One is the roller support. It can offer only 1 support reaction maximum. I have taken that. Okay. Anything else? So everything done, right? Now how to get the reactions? So now it's a straight one. What is that? First, x direction, static or dynamic equilibrium. Static equilibrium. So sigma fx is equal to 0. Now tell me, what are the forces in x direction? Sir, before going to this step, I didn't do here. Before going to this, do one thing. What is that? Check whether all the forces are in x and y direction or not. Okay. So see, this, all these are in x and y direction except my W2. So what to do? Resolve this. So what will happen if I resolve this? The component of force in this direction is how much? This is which side? Adjacent side. So it is cos component, W2 cos theta. And the component of force along this direction is how much? W2 sin theta. Have you got everything? Okay. Now tell me, what are the forces in x direction? RAX. It is in the positive x direction. So RAX. Next, W2 cos theta, that is in negative x direction. So minus W2 cos theta is equal to 0. Let us say this is equation 1. Next, y direction. Again, static or dynamic, sir, all trusses are at rest. They are not going to be moving because they are structures. They are not some vehicles, right? They are not moving. They are all at rest. So always they will be in static equilibrium. Are you okay? So in y direction, as it is in static equilibrium, what to write? Sigma Fy equal to 0. Tell me, y direction, what is that? Static equilibrium, sigma Fy equal to 0. Ray, upwards or downwards? Upwards. So plus Ray. Next, W1, downwards, minus W1. W3, downwards, so minus W3. W2 sin theta, that is also downwards, so minus W2 sin theta. Next, RBY is acting upwards, so plus RBY is equal to 0. Let us say this is equation number 2. Next. X direction done, y direction done. Next, moment. Static and dynamic? Static. So what I have to write? Sigma m with respect to some point, any point, your wish. Okay. But which is the convenient point? More unknowns and more forces are there only at this A. So I will take this as my reference point. I'll take this as my reference point. Okay. So I'm sitting here. Moment due to RAX. Moment due to RAX. 0. Moment due to RAY. 0. Next. Moment due to W1. Moment due to W1. What will happen with moment due to W1? See. If I extend the line of action, right? If I extend the line of action, see, what is this angle? See, take this triangle. All are equal. So all are equal. So this is how much? Equilateral triangle, 60 degrees. What's the angle? 60 degrees. 60 degrees. So as this is 60 degrees, how much this will be? How much this will be? You can take like this also. Say this is a right angle triangle. So L cos 60. Cos 60 is 1 by 2. And exactly the altitude is falling here exactly at the midpoint. From that also you can say this is L by 2. Either from that or from L cos 60 it is L by 2. Okay. So it's at a distance of, the shortest distance is L by 2. Now this is the position vector. This is the position vector downwards. Clockwise or anti-clockwise? Clockwise. According to us, minus L by 2 into W1. L by 2 into W1. Next W3. Next W3, right? See, this is at a distance of L. This is the position vector. Clockwise and anti-clockwise? Clockwise. So, minus L into W3. Next, go to this. W2 sine theta. This is the line of action. This is the line of action. See, L. This is again same equilateral triangle at the half. So, it is L by 2, right? So, L plus L by 2. 3L by 2. Now, this is the position vector. This is the position vector. How is it turning? Again, clockwise. So, minus 3L by 2 W2 sine theta. 3L by 2 W2 sine theta. Next, this one. They see, not only this one, we have one more here. What is this? W2 cos theta. Now extend this. This is the line of action. Now what is this distance going to be? See, if this is 60, what is this height going to be? See, 60 degrees, this is L. This is L cos 60. So this is L sin 60. L sin 60 is root 3L by 2. This is root 3L by 2. Now, this is the position vector. How is W2 cos theta? See, for W2 sin theta, it's down like this. But W2 cos theta, like this. So, it is which direction? Anti-clockwise. So, plus, what's the difference? Root 3L by 2, W2 cos theta. So, W1 done. W3 done, W2 sin theta done, W2 cos theta done. Next, last one, RBY. It's at a distance of 2L, right? This is the position vector. How is it rotating? Clockwise. According to us, clockwise is minus 2L into RBY. So, from this equation, this is the third equation, I can get RBY. From RBY, if I substitute, I can get RAY. And here I will get RAX. I can get all the three support reactions, RAX, RAY, and RBY from the three equations. Now, I'm not going to solve because they are only in the letters W1, W2. Their values are not given. I'm not going to do it. Okay. So, this is the procedure by which you can find out the support reactions. Okay. So, the first step, what's the first step given to me? Consider the entire truss to be a single body and find the support reactions. That task is done. Okay. All of you. Next. Go for the next step. That is step 2. Step 2. Draw the free body diagram of joint of interest. Draw the free body diagram of joint of interest. Draw the free body diagram of joint of interest to which the member is attached or joined, or the member is connected, or the member is joined, or okay, so the member is attached. Listen. Draw the free body diagram of joint of interest to which member is attached. Listen. What do you mean to which member is attached? I'm interested in which member, sir. For which member I want to find the support reaction. Sorry, load. In which member I want to find the load? In the member C. He told, draw the free body diagram of joint of interest. That means your interest. But what's the condition he kept? To which the member is attached. See, member is attached to which joints? See, my member is C. So it is attached to joint C and is also attached to joint E. It is attached to joint C and joint E. So draw the free body diagram of either joint C or joint E. The condition is what? It should be attached to that member. It is attached to that member is C and E. And which one? Your interest, joint of interest, right? So which one we want to write? It's up to you. It's up to you, right? Your wish. C or E. Based on our requirement, we will go with it. Okay. So shall we go with A, C or E? Anything is fine, sir. Anything is fine. Okay. So I will go with, let us say C. Let us say I will go with C. Okay. Now, what's the next step? What's the next step? Draw the free body diagram of joint of interest to which the member is attached. So I'm drawing the free body diagram of joint C. At joint C, what is there? Nothing is there, right? It's not a body, it's only a pin. It's only a pin there, right? It's a point, right? I'll take only a point. I'll take only a point. How to draw a free body diagram? Free the body from everything and draw the sketch. Next, actions. Next, reaction. So what I'm taking? Free body diagram of C. I'm drawing the free body diagram of joint C. Free body diagram of joint. Free body diagram of joint C. Now, free the body from everything and draw the sketch. I'm taking only a point because it's only a point. Okay. Next. Actions. What are the actions? At joint C. What are the loads acting? Only one load is there. What is that? Only one load? W1. How is the W1 acting? Vertically downwards. Okay. W1 vertically downwards. Done. Next. Any other actions? No actions, only W1. Done. Next, reactions. What are the reactions? See, at joint C, I have connected with members. AC. I have connected with members AC. Next, CE and CD. There are three members connected. AC, CE and then CD, right? Three members are connected. So what happens because of the members? Sir, whenever there is a member connected, the load applied by the member will be along the member. It can be a push force or it can be a pull force, but it will be along the member because it's a hinge joint. You make a hole and you attach it. See, whatever direction you apply, it will rotate. Whatever direction you apply the load, it will rotate. Either you can pull or you can push the joint. Either you can pull the joint or push the joint. Remaining whatever you do, it will rotate. So I cannot apply the load in any other direction except this one. Okay, and I will give the proof of it also. After the analysis is done, I will have to give some 2-3 proofs. In that, I'll give that one proof, and I'll also show that that's right. There's a reason why it's having only axial stress. That means whether the member will be under compression. See, if it is pulling, it will get elongated. If it is pushing, then it will get compressed. What happens? We'll see in the end of the analysis. But for the time being, what I'm saying, what's it I'm saying? The load will be only acting along the member. It cannot apply anywhere other than that. So the load along the member will be along the AC will be along the member. This is the line of action. The load, whatever the load is coming, the reaction coming because of the member AC is along the line of action of that load is along the AC. Now, is the force towards C or away from C? Is the force towards C or away from C? Generally, if it is a contact to surface and contact, I'll say the normal reaction will be always a push force. But here I cannot say. It may pull or it may push. I'm not sure. Sir, by experience, people can say what will happen, but I won't suggest that. It can be anything. Sometimes it may go wrong. It can be anything. Then what to do, sir? Generally, what I follow is I will take the loads always towards the joint. I'll take always towards the joint. If it comes positive, I am correct. It is always towards the joint. If it is coming negative, it's wrong. It will be away from it. Always I will follow that convention. If you want always away, you take it away. I don't have any objection. The convention what I will follow is the load along the member AC is always towards the joint. Whatever joint is my interest, I'll take always towards the joint, and it will help for me in the stress analysis. How is that? I will show in the end. Okay. So 2 points. One is why the load is along the member. That is why it is having only axial stress. How it got it. The second is why I am taking it always towards the joint. There is no rule, sir. See, if you open a book, some people will take one in, one out and all based on experience they take. Some people will take always away. Some people will take towards the joint. What I prefer is towards the joint. It's not a condition in any textbook. Don't ask me, sir, nobody has told it. Why? I will tell you in the end how it helps for you. Okay. So for the timing was that the load along the member AC is always towards the joint. I'm taking always towards the joint. See, the member AC, it is like this. It is like this. The member AC. Okay. See, this is how the member. I'm taking always the load towards the joint, towards the joint, towards the joint. I'm taking the load always towards the joint. Okay? Okay? Next. It's also connected with another member. What are the other members? See, what is this member? F. See, what's the member? AC. So the load in the member, the load in this member is what I will call F, AC or CA. Whatever you write, I don't have any objection. AC or CA. It's okay, fine. Next, what's the next number connected to it? There's one more number, that is CE. CE. What is that number? CE. The next number is CE. So the load in the member will be always along the member and towards the joint. Why towards the joint? It may be or may not be, I don't know, but it will be given in the end of the problem. If it comes positive, it will be towards the joint. My assumption is correct. If it is coming negative, that means my assumption is wrong and it is not towards the joint. Okay, so how many members are connected there? 3. What are those 3? AC we have taken already, CE already taken. One more is there, that is CD. How is CD? Horizontally. So the load will be on this horizontally. Sir, if it is pulling, it is away. Yes, sir, it is away. So, automatically the answer, whatever you are going to get, that will become negative. Okay, then I will change. But now I don't know. It can be a push or a pull force. It can be compression or tension. So, I'm taking it always towards the joint. If it comes positive, because see, if you take something in the exam, after getting plus or minus, you will get a confusion on now what is happening, whether it is positive. Don't have anything. Just take towards the joint. If it is coming positive, yes, my assumption is correct, it is towards the joint. If it comes negative, no, my assumption is wrong, it is away from the joint. That's it. No need to come back and check what I have taken and all. The end, positive, yes, I am correct towards the joint. Negative, no. That's what. I will never come back and see, sir, what I have taken and all. Okay, so follow the same constraints. Or if you take always away, you take always, but only follow one notation. Okay, so draw the free body diagram of joint of A in truss, to which the member is attached. So I want to find the load in the member CE. So the CE is attached to either CRE. So draw for CRE. I have drawn for C. And I got the free body diagram. Okay. Okay. Now. What is the next target? See, what is this system? What is this system? Coplanar concurrent force system. Are yes or no? For a coplanar concurrent force system, how many equations of equilibrium we have? Because it's a point, it can have only translation. That means it can have only 2 equations of equilibrium. Yes or no? For a coplanar concurrent force system, I have only 2 equations of equilibrium. How many? 2 equations of equilibrium I have. 2 equations of equilibrium only I have. Okay. Now, how many unknowns are there? I don't know FAC. I don't know FCE. I don't know FCE. But I know W1. That is given load. But how many are there? 3 unknowns are there. How many unknowns are there? 3 unknowns are there. 2 equations of equilibrium and 3 unknowns. 2 equations of equilibrium and 3 unknowns. Can I solve? No. Then what to do? While selecting the joint, take care. There should not be more than 2 unknowns. Now go back and see here. Either take the joint C or E. He gave the option. At joint C, 1, 2, 3 unknowns are there. If suppose I have taken E, how many unknowns are there? 1 FAE, then FCE, then FED, and then BE. How many are there in total? 1, 2, 3, 4 members are connected there. 4 unknowns are there, only known as W3. So 2 equations, because again it is a CCFS, coplanar concurrent force system. 4 unknowns, 2 equations. Again I cannot solve. Then what to do? So if there is generally when we prefer method of joints is only when the member is attached to those joints where there are not more than 2 unknowns, then I go with method of joints. Otherwise, I will prefer method of sections. But still with the method of joints also, you can solve the problem. How to solve it? Listen. Sometimes it is convenient, even though there are more than 3 unknowns, to go with method of joints. So what to do? Listen. See, I don't know how to solve C. I don't know how to solve E. Now go to the nearest joint. Where there are not more than 2 unknowns. See, if I go to D, 1, 2, 3 are there. If I go to B or A, whatever you go, right? How many are there? 1, 2, 1, 2. But if I solve B, again at E, even though I know BE, there are 3 more. So this is not preferable. What is preferable? Go to A. How many are there? AC, AB. Now solve this. I know already the support reaction RAX, RAY. In the first step, I got RAX, RAY. Now, what are the only unknowns? AC, AE. So, find out those two unknowns, AC and AE. If I know AC, now go for the join C, find out the remaining two unknowns. Then you will get C. You will get FC. Are you getting me? So, what's that? What do you have to do? Take care that while selecting the joint, that not more than two unknowns are created. Not more than two unknowns are created. Are you getting me? Not more than two unknowns are created. If suppose, for the member, if there are no joints with not more than two unknowns, then what to do? Go for the nearest to joint and find out the unknowns there. Then slowly go to the joint which is having, go to the nearest to joint which is not having more than two unknowns, then come back and solve the joint of interest. Are you okay? So in this problem, what I have to do? First to solve the joint A, then find out AC, then go and get the FC. Okay? So this is the method of joints. Okay? So this is how we will do. First step, consider the entire truss to be a single body and find out the support reactions. Then, draw the free body diagram of the joint of interest for which the member is attached. Okay. Now, take care. Now, what's that? Take care while selecting the joint, not more than two unknowns are created. Not more than two unknowns are created. Sir, if there is no possibility, then what to do? Go to the nearest to joint which is having not more than two unknowns, and then from slowly come to the joint where you can reduce them. Where my member is attached, and then solve that joint. Okay, here go with A, then you know FAC. Now, if you know FAC and W1, then only left to be CD and C. Then we can solve it. Okay, so this is all we have in method of joints. So the remaining steps I will write down. All the forces, both actions and reactions, all the forces, both actions and reactions at a joint, all the forces at a joint will comprise of a coplanar concurrent force system. All the forces, both actions and reactions at a joint will comprise of a coplanar concurrent force system. So what is that I can write? For a CCFS, I'm continuing this. For a CCFS, we have two equations of equilibrium. We have two equations of equilibrium. For a CCFS, we have two equations of equilibrium. I have explained all these things. I'm just writing the steps. We have two equations of equilibrium. Therefore, at maximum, two unknowns can be solved at a time. Therefore, at maximum, two unknowns can be solved. Therefore, at maximum, two unknowns can be solved at a time. Therefore, at maximum, two unknowns can be solved. So, if I have more than two unknowns, what to do? Hence, start the analysis. Using the joint. And start the analysis using the joint where there are not more than two unknowns. Hence, start the analysis using the joint where there are not more than two unknowns. And proceed towards the joint of interest. Okay, so this is the procedure. We will apply this and solve the problems. Once we will finish method of sections also, then we will go and do it. Okay, hope you have gained some knowledge from my lecture. If you feel so, please subscribe to the channel. Please leave your valuable feedback and doubts in the comment section. For my complete video lecture series, enroll in OCTEMY. Thank you. Let's catch you soon in OCTEMY. Have a good day.